Okay. So, yeah, maybe before I do this example, let me just show you in the book. This is page 507. Um, just what the formal definition of stability is, because I've been pretty informal so far. Um, so we say that a critical point, and this is the same as what I was referring to as an equilibrium point. We say it's stable if for each epsilon greater than zero, there's a delta greater than zero, such that if um, if x naught, which is our initial condition, so if the vector that we're starting at is within delta of x star, then the solution to our differential equation is going to always stay within epsilon of x star. In other words, roughly speaking, this just means that if you start out close enough to x star, then you're never going to get too far away from x star. And this is why we consider it stable if there's like an orbit, like if the solution to the differential equation just goes around and around a certain point, like the type that we saw that was just tracing out an ellipse. Maybe it's not necessary to show you, but I started flipping pages, so yeah, I would call this a stable equilibrium point because once again, if I start out close enough to this, like the center of the ellipse, if I start out close enough to it, I'm never going to get too far away. I may move a little bit away, like if I start here, then my orbit is going to take me here, which is a bit farther from the center than from where I started. But I'm not going and going and going. I'm never going to get too far from the center. I'm never going to get farther than this. So we consider that stable. However, obviously, maybe that's not completely satisfying our intuitive notion of stability. We also have what we call asymptotically stable. Asymptotically stable means that you're moving towards x star. You're not just going around and around. Asymptotically stable means that if you start out within delta of x star, then actually the limit as t goes to infinity is approaching x star. So in other words, you get as close as you would ever want to get to x star as t goes to infinity. And that is more like if you're spiraling inward, for example, that would be asymptotically stable because you're getting closer and closer. You don't really have to be spiraling inward. You could just be moving more like directly inward. Uh, like, yeah, like this picture. That would also be asymptotically stable. And of course, this one would be unstable. You're moving away from the point. Um, so, right. Let me then. Basically, there's theorem 1, and I'm on page 518 now. Theorem 1 is basically now a summary of what we said, and I just wanted to tell you what asymptotically stable and stable meant, just so you could understand what theorem 1 is saying. But so that just summarizes what we said about the various ways that the eigenvalues could be and what that means for the stability and asymptotic stability of the critical point 0, 0. Um, there is also now almost linear systems. So, and this is, by the way, this is 9.2 now. And right, like we're talking about technically nonlinear systems. So x prime, it's not ax plus by, it's just some function of x and y. And y prime is also some other function of x and y. But what you do is you find a linear approximation of these functions, and then to determine the behavior of the solution near an equilibrium point, you essentially treat it as though it behaves the way a linear system would behave near that point. So let me do, am I ready to do an example? Yeah, well, let me start talking about an example. So let's investigate this stability and equilibrium point type of stuff. Let's investigate this for a nonlinear system. So this is taken out of the book exercises. This is number 19 out of 9.2. And we are given the system x prime is this, y prime is this. This is nonlinear because there's these x times y terms. And so the instructions that I'll give us is to find all the critical points or equilibrium points and investigate the stability of 0, 0. So what we're going to do is treat this like the system so what do I want to say first? Actually, okay, hold that thought. Let me just find all the critical points first, because I don't need to talk that much before I do that. Critical points, once again, it's just when these equations are both 0. So this is a neat exercise that goes back to, really, you could say, elementary algebra. I don't like nonlinear systems. I like linear systems. What's nonlinear about this? The x times y term. I would like to cancel that. So I'm going to take this equation plus 2 times this equation. I get x plus 8x, 9x. I get negative 3y minus 12y is negative 15y. This goes away. That equals 0. Let's see. X equals 15y over 9, which would be 5y over 3. Okay, let me plug that somewhere where it might help. 5y over 3 minus 3y plus 2. 5y over 3y equals 0. Whoops. Now, yeah, so this is like 9y over 3, so negative 4y over 3 plus 10 thirds y squared equals 0. Let me just multiply everything by 3 because I hate fractions. And now I can go, why don't I factor out 2y, and then this will give me 5y from here, minus 2 from here. So basically y equals 0, or y equals 2/5 from this. And then I want to find points, so x is 5y over 3. So in this case, x would be 0 when I get the point 0, 0. In this case, y would be 2/5, so x would be 5/3 times 2/5, so 2/3. So this system has two equilibrium points, 0, 0, and 2/3, 2/5. Okay, now basically the instructions told us that 0, 0 was going to be a critical point, because we're specifically supposed to investigate the stability of that. So what are we going to do? We are going to, like I was starting to say, we are going to treat this system as though it is linear. Right. So, like, this, right, yeah, sorry, I'm fumbling with my words here. If I call this function f of xy and this g of xy, I take some partial derivatives. Like the partial of f with respect to x would be 1 plus 2y. And I evaluate these at the point in question. So I get 1. Partial with respect to y is -3 plus 2x. And I evaluate this at this point, so it would give me -3. I do g. This gives me 4 minus y. And then evaluate it at that point. I get 4. Partial with respect to y is, let's see, -6 minus x. And then at the point in question, that gives me -6. So, roughly speaking, I'm going to treat it like the following system. These are going to tell me the coefficients for f. When I did the partial with respect to x, I got 1. When I did the partial with respect to y, I got -3. So that gives me these coefficients, the 1 and the -3. And then when I did g, for y prime, when I did g, I did the partial with respect to x and I got 4. I did the partial with respect to y and I got 6. So what we just did is we call this, we just linearized the system near the point near the point 0, 0. We linearized it. And what we have, the tool that we have, just to be formal about this, So what we have is an almost linear system, and I won't go into too much detail about this. The book does say something formal about what does it mean to be almost linear and when can you use the linearization. There is like a technicality here where you have to be able to write these functions with a remainder, and this limit has to be 0. For us, what happened, basically what happened is when we linearized the system, the xy terms just dropped, right? Because if I go down here, it's actually the same thing, just without the xy terms. I mean, it's just 1x minus 3y. That's what I would get up here if I just dropped that term. And for y prime, it's the same. So these things that got dropped, basically what we're assuming is that those are negligible. And this is why in this box you can check that these things actually are negligible. So I'm not going to talk about this a lot. This is normally for nice functions. If we're dealing with nice situations, it's just going to be true. So we're not going to spend a lot of time checking it, but you can check it. These things are negligible in the sense that if I take the xy term, well, except I'm plugging in u and v, and I divide it by this, I'm checking this condition that goes to 0, and it does. So, right, this is an almost linear system, and what we have is theorem 2. You make the associated linear system, which is referred to in theorem 1, where we summarize what happens for linear systems. You make the associated linear system, like we just did, and then this tells you what to do with the, what are the various cases involving the eigenvalues, whether they're both negative or one of them's positive, or if they're imaginary. By the way, this theorem 2 uses some terminology that is more detailed than what I'm really into. Nodes and spiral points, those are just types of critical points or equilibrium points. I won't define these formally. Of course, spiral point is what it sounds like. A spiral point is an equilibrium point that behaves like a spiral, whether it's like spiraling inward or spiraling outward. A node is a type that doesn't do that. A center is like a center is one where it's just like an ellipse. It just goes around and around and it comes back to the same spot where it started. That's another type of equilibrium point. I'm not defining these formally. I just want you to know that these are types of equilibrium points, and this theorem characterizes them. Anyway, let me finish this example. I need another piece of paper, because this one's not that hard. There are, for these theorems that I'm showing you, there's maybe, it seems like there's a lot of cases, but this isn't that bad. So what are we doing? We're talking about this linear system, and we know we can characterize linear systems according to the eigenvalues of the associated matrix. So, I want the eigenvalues of 1, -3, 4, -6. And this is an easy problem, so this will be like a vacation for us. It's like that. I multiply these. 1 minus lambda, negative 6 minus lambda, plus 12. This would give me lambda squared. Let's see, I've got a plus 6 lambda and a minus lambda, so plus 5 lambda. I would have a minus 6 and a plus 12, so I'll write plus 6, which is lambda plus 2, lambda plus 3. So lambda is negative 2, negative 3. So what do we see? Both negative. They're not complex. If they were complex, then I would just check the real part to see whether that was positive or negative. But these are two real. What do we see here? If I check theorem 2 carefully, let's see. We're not in case 1 because it's not two equal eigenvalues. We're not in case 2 because they're real. So that means we're in case 3. So otherwise, basically, this just tells us that the answer is the same as theorem 1 would tell us. So I look to theorem 1, and what do I see? Asymptotically stable if the real parts are both negative. So we're good. Well, I guess we would be good no matter what. We were just looking for what was our final solution. So how should we write this? I guess the instructions just said investigate the stability. So I'll just write some some reasonable conclusion. So 0, 0 is an asymptotically, I can just spell that, stable equilibrium point. All right.